So by way of preface, my training and background is as a theoretical computer scientist, but this is going to be a mostly non-technical talk. I know it's a diverse audience, and I'm going to talk about the ideas that we discuss in a book that I've written with my good friend and colleague Michael Kearns called The Ethical Algorithm, in which we talk about an emerging science of attempting to embed ethical norms into the design of algorithms. And I'll note at the outset that a lot of this interesting science is being done right here at Yale. So the starting point is, I think, something that maybe everyone here is already aware of, which is that we are increasingly using algorithms derived from machine learning in consequential domains. So it used to be maybe 10 or 15 years ago that we used machine learning, but it was mostly for things like spam filtering or maybe targeted advertising, in which the consequences of mistakes were pretty minor. These were sort of low stakes applications of machine learning. But as machine learning has become better, and as we have, as a society, started collecting increasingly rich data sets about people, about individuals, sort of the digital exhaust that you generate every day when you use the internet, we've started deploying machine learning in domains in which it makes really consequential decisions about particular people. So for example, human resources departments in big companies now use machine learning to screen resumes. They use machine learning to guide hiring and compensation decisions. Credit, if you apply for a credit card, your application now may never be read by a human being. It might be automatically approved or denied by a statistical model that was trained using the principles of machine learning. Criminal justice, in many states, including Pennsylvania, machine learning algorithms are used to inform bail and parole decisions. They're used to deploy police officers and using predictive police algorithms. And at this point, it should be no surprise that as we use machine learning for these consequential tasks, of which, we use machine learning in pipelines in which, back when it was only human beings in these decision-making pipelines, we expected them to respect certain ethical norms like fairness or privacy. It should come as no surprise, since historically these norms haven't been part of the design process of machine learning algorithms, that we see bad things happen, that we see deployed algorithms that appear at least to actively be discriminating against certain populations, that appear to violate privacy. And by now, there's a number of excellent books that do a good job of cataloging the problem, that do a good job of convincing you that this is a problem, and have a number of compelling anecdotes. But when it comes to proposing solutions, by and large, these books say extremely sensible things like, we need to rethink regulation. But the reason we wrote our book is there's sort of this complementary approach, which is actively being developed in computer science and statistics departments, including at Yale, which is that if we think about what are the bad behaviors that we want to prevent, then we can try to design the algorithms to be better in the first place, so that the algorithms that we deploy don't violate these norms of fairness and privacy, while hopefully allowing us to still get some of the benefit of machine learning, which is, after all, a powerful and useful technology. And so that's what our book's about. Now, I want to start by talking about this phrase that appears in our title, ethical algorithms, which might seem like an oxymoron, because an algorithm, after all, is a tool, much like a hammer. It is ultimately designed and deployed by a human being. And if you think about hammers, you know, these are useful tools, but they can also be used for bad things. They can be used as instruments of violence. And yet, like, we wouldn't think of this as a failure of the hammer, like we wouldn't impart any kind of ethical character on the hammer. And I wouldn't be here talking about ethical hammer design. And so I want to start off by like thinking, you know, are algorithms any different than hammers in this sense? And I'm not going to propose that algorithms have any kind of ethical character on their own, but I do want to try to briefly convince you that it is important to try to embed ethical considerations into algorithms in a way in which it is not important to try to embed them into hammers. Okay, so what's the difference between an algorithm and a hammer? And I'm using the word algorithm a little informally here almost entirely throughout this talk. When I say algorithm, what I really mean is a trained model, something that is the output of the machine learning pipeline. And the thing about the algorithms that are trained using the principles of machine learning is that, unlike the algorithms that might be involved in, say, a word processor, you know, there's nobody who sat down and coded what these algorithms should do in every eventuality. Okay, so let's briefly recall, you know, a bird's eye view of the machine learning pipeline. If you are going to train an algorithm using the principles of machine learning, the thing you will start with is data, and usually a lot of it. So in a modern machine learning application, you might have collected a data set that contains the data of millions of people. From each person, you might have thousands or even tens of thousands of features. And, you know, at best, you understand how this data was gathered, but it's extremely hard to understand the, you know, all of the content of such an enormous data set. Okay, but your starting point is a data set. And what do you do with it? Well, usually what you do is you define some objective function that you'd like to optimize, some objective function that you would like your algorithm to excel at. And usually this is some relatively narrow proxy for classification accuracy, or maybe click-through rate if you're targeting advertisements, or maybe profit. But the point is, it is some relatively narrow mathematical expression. And then you sort of set loose a machine learning algorithm, something like stochastic gradient descent, that will essentially relentlessly search through an enormous class of models or algorithms, attempting to find one that excels as measured according to the narrow objective function that you specified. And the output of this process can be enormously complex. If you're training a deep neural network, then the output of this process might be a vector of, you know, millions of numbers. People are training models now that have billions of parameters. And at this point, it's very hard to say anything at all about what these algorithms do, except that they are likely to be extremely good as measured according to the objective function that you set out. Because after all, that's how we came up with this model. We searched through an enormous space of models, trying to find the one that was best as measured by our narrow objective function. But if our narrow objective function turned out not to capture absolutely everything that we wanted, if it was possible to optimize our objective function in a way that might harm a person or systemically harm a collection of people, there's no reason to think that the algorithm that we get out won't do that. And in particular, it's extremely hard to predict whether it will or will not do something that is not exactly captured in the objective function of the algorithm. And that's sort of the crux of why algorithms, especially those derived from machine learning, are different than hammers. That is, if we want our algorithms to respect ethical norms, it is necessary but not sufficient that the people deploying these algorithms themselves be ethical. For a hammer, you know, it's sort of enough that the person wielding the hammer is ethical. But because of this machine learning pipeline, it might be, and I would conjecture it often is, that the scientists and engineers designing and deploying these algorithms, have no ill intent at all, and that sort of the litany of high-profile fairness and privacy violations we've seen over the years are really the unintended and unanticipated side effects of this process. And so the premise of the book is that if we want to fix this, if we want to be able to design and deploy learning algorithms that respect social values like privacy and fairness, it's not enough to make sure that the people deploying these algorithms respect these social values. We have to think very precisely about what we mean by these things, and we have to attempt to embed notions of privacy and fairness into the algorithms themselves as mathematical constraints, for example. And this is hard, right? Because privacy and fairness are complicated things. They don't mean just one thing. And it will ultimately be impossible to encode everything that we might mean by privacy or everything that we might mean by fairness into a single mathematical constraint. Nevertheless, I want to argue that it is an important exercise to try and identify certain aspects of privacy, certain aspects of fairness that we can think about in a mathematically precise way, for two reasons. First, doing so might sharpen our intuition and allow us to find problems or contradictions with our intuitive notions of privacy and fairness. And this is something that we've seen happen in the literature already. And second, because it's sort of a necessary prerequisite to constraining machine learning algorithms, which are in the end the output of mathematical optimization procedures, that we be able to enunciate our concerns for violations of privacy or a lack of fairness in a mathematical way. And so I've written a bunch of social values here, things like privacy, fairness, accountability, interpretability, in increasing degrees of grayscale, roughly, I think, in proportion to how much we can say about them as a field so far. So we definitely don't understand everything there is to know about privacy. Privacy is not a solved problem, but we've made great strides. I think that this agenda of trying to code social values in the form of mathematical constraints and see how far we can derive use of data while respecting these norms. This agenda has been most successful so far in the domain of privacy. For fairness, we're not there yet, but I think the field is off to a good start. And these things lower down, accountability, interpretability, these are important problems, but I'd say that they're really in their infancy. We don't, computer scientists, there's lots of people working on these things, but I think we're at a point at which we haven't found the right definitions. So these are sort of areas that I hope will see some of the success of privacy and in part fairness maybe in the coming years. Okay. And so let me talk about privacy, and since I want to convince you that a lot of the art here isn't coming up with the right definition, let me walk you through a brief history of the study of data privacy, starting with bad definitions and getting up to what I think are good ones. And so in the dark ages of data privacy back in the 1990s, and to some extent still today, people used to think about data privacy through the lens of anonymization. The idea was, if I have a data set of sensitive records, maybe I've got medical records, it's okay for me to release those so long as I scrub the records of people's names and other identifying information like social security numbers. Okay. And so this is exactly what the Group Insurance Commission of the state of Massachusetts did in the 1990s. They released a nominally anonymized data set of hospital visits for all state employees in the state of Massachusetts. And this wasn't a security breach or anything. This was a data set that they were intentionally releasing so as to allow medical research. And they were definitely aware of privacy concerns. And so they sort of carefully scrubbed out names and social security numbers and anything else they thought might be a unique identifier. But they left in basic demographic information. So they left in age and gender and zip code, because these, first of all, are not uniquely identifying. There's many people with your age, there's many people with your gender, there's many people with your zip code. And second of all, are useful for demographic research. So the problem is, while it's true that none of these demographic attributes are uniquely identifying on their own, in combination they can be. And so LaTanya Sweeney, who was at the time a PhD student at MIT and is now a professor at Harvard, noticed this. And what she discovered was that if you took the triple of age and gender and zip code, this would uniquely identify a very large fraction of people in the data set. Meaning, if I look at all of the people who have your particular age and your particular gender and your particular zip code in the data set, for many people, there was only one record matching that triple. Now, there were no names attached, but the problem with being able to uniquely identify people is that you can now start to cross-reference data to try to figure out who's who. And so Dr. Sweeney did this. She realized that there was another public data set, the voter registration rolls of Cambridge, Massachusetts, that had voter names together with their age and gender and zip code. And she was able to identify the medical records of Bill Weld, who was the governor of Massachusetts at the time, and to make a point, she sent his records to his office. And so this was sort of a big deal at the time. This made people realize that anonymization is very difficult. Just removing unique identifiers doesn't work because there's all sorts of extra information out there that you can attempt to cross-reference a data set with and re-identify it. And the next 10 years of research on data privacy, I think, somewhat unfairly characterize as a cat and mouse game between privacy researchers and attackers, in which the privacy researchers were sort of proposing syntactic constraints that would try to foil whatever was the most recent attack that an attacker had thought of. And then a more clever attacker would come around and show that the most recently proposed constraints of the privacy researchers really weren't good enough. And the problem with this back and forth was that nobody tried to define what privacy should mean semantically. They were proposing just these syntactic constraints to screw up whatever was the sort of most recently published attack. And so let me talk about just one of these syntactic constraints called k-anonymity to sort of demonstrate what can go wrong. So the premise of k-anonymity was the following. People realized that LaTanya Sweeney's attack was based on finding combinations of demographic attributes that uniquely identified someone, right? In the Massachusetts records, if I knew your age and gender and zip code, the problem it seemed that you could be uniquely identified in the data set with this triple. And so the premise of k-anonymity is to just make sure that can't happen. Okay, that if I am too anonymous, if my data set is too anonymous, then any collection of demographic information will match at least two people. Or if my data set is 3 anonymous, any collection of demographic information will match at least 3 people. And you can accomplish that by hiding information. So for example, rather than reporting age exactly, I might report it in a bucket of 10 years. I might withhold some of the digits of the zip code. And so for example, if I know that my 56-year-old female neighbor is a patient at the hospital of the University of Pennsylvania, and they release a too anonymous table of their patients, you know, I know the age and gender of my neighbor. I know her zip code because she's my next door neighbor. But the promise of true anonymity is, despite that fact, I cannot match that information to just one record. If I matched it to one record, I'd know it was her, but true anonymity promises that whatever I know about her, it'll match to at least 2 records. Okay. And so already you might think that this isn't capturing everything that we might want from a privacy definition, because even though I can't uniquely identify my neighbor's record, you know, I can match it to these 2 records, and now I know that she either has HIV or colitis, and maybe already something she didn't want me to know. But the problem goes much deeper than that. So for example, suppose that I also know that she's a patient at Pennsylvania Hospital, which is another hospital down the street. And suppose they've released a 3 anonymous table of patient records. Well, again, I can look at their table and I can't match her demographic information to a unique record. It matches, you know, at least 3. But now I can cross-reference these 2 tables and notice that there's only one record that matches between these tables. And now again, I've re-identified her record. I've figured out her diagnosis. And so the problem here is that this attempt at anonymity entirely falls apart in the presence of extra information that might be out there, which is ultimately exactly the same problem that anonymization had. And so sort of a catchy phrase that is due to Cynthia Dwork is that really anonymized data isn't. You know, either you haven't anonymized the data. You know, you think you've anonymized the data, but there's some clever attacker out there who can in the end re-identify data, because you know, it's hard to predict what auxiliary source of information they might have now or in the future. Or if you've really prevented this, you must have removed so much information about your patients, say, that it's not really data anymore, that you've got no useful information at all. And so this turned out not to be a good collection of definitions. And the problem is really that there was no attempt to define what privacy meant, right? There was just an attempt to prevent the last attack. And so let's go in the other direction. Let's think about a definition that tries to define what privacy means, but proposes something a little bit too strong. Okay, so we might think to ourselves, okay, like, what should privacy mean? Maybe what it should mean is that, you know, say a statistical analysis or a medical study is private. If nobody can learn anything about me or anyone else in the study that they didn't know about me before the study was conducted. Okay, if we could promise that, that would be an extremely strong guarantee of privacy, right? It would mean that whatever was published as a result of my data really like revealed nothing at all about me. And I claim that this is actually a bit too strong, and to understand why, let's you know, maybe imagine that you were one of the 2/3 of physicians who participated in what came to be known as the British Doctors study, this collection of studies by Dahl and Hill that were the first to conclusively demonstrate a link between smoking and lung cancer in the 1950s. Okay, so if you were a physician in this study, you know, well, let's say you were a smoker, you probably, you know, weren't hiding the fact that you were a smoker. There was nothing to be ashamed of being a smoker in the 1950s. So this was a publicly observable demographic attribute about you. And after the study was published, you know, we, the world, knew something that we didn't know before. We knew that there was a significant correlation between smoking and lung cancer. And so in particular, because we already knew you were a smoker we knew something new about you. We knew that you were at increased risk of lung cancer. And this is like this is something that could really cause you like concrete harm. For example, if you lived in the United States, this would likely cause your health insurance rates to go up. Okay, so like this study resulted in a new fact being learned about you that resulted in like concrete dollar harm. And so the question is, should we really think about this study as being a violation of your privacy? And I want to argue that the answer is no, for a couple of reasons. So first of all, a practical reason. If we were going to take the position that revealing that there's a link between smoking and lung cancer is a violation of the privacy of people in the study, then this would really mean that nothing at all could be done with data in a private way, right? This is exactly the kind of thing we want to do with demographic data. We want to uncover correlations between different attributes. And if that results in a privacy violation, and this can be formalized, really any analysis of data at all would be a privacy violation under that definition. But there's also a better reason, which is that the fact that we learned something new about you, the smoker, when this study was published, really had nothing to do with the fact that your data was used in this study. Right? If you were a smoker, if you were one of the physicians who didn't participate in this study, we would learn just as much about you, right? In fact, if you hadn't even been born in the 1950s, if you were born later and are subsequently a smoker, again, this study like disclosed something that caused society to learn something new about you, right? And so it's going to be sort of weird if we're going to imagine that data analyses that were conducted entirely without your data, maybe even before you were born, were violations of your privacy. And the reason is, in this example, the new facts that we learned about you really didn't derive at all from your data. It derived from some population-wide correlation, some fact about the world, that there's this association between smoking and lung cancer, that because it is a broadly true fact about the world, could have been learned, in fact, was learned without your data in particular. Okay, and so this is pointing to a subtlety here. We, when defining what we mean by privacy, need to try to disentangle information that might be learned about you merely because of facts about the world, merely because of general population-wise correlations, and information that is disclosed about you really corresponding to your secrets, to information that was encoded in your data in particular. And this is exactly what differential privacy, a mathematical notion of privacy introduced in 2006, aims to do. And so, this idealized notion of privacy we talked about with respect to the British Doctors Survey, you can think about it as comparing two counterfactual worlds, right? The British Doctors Survey notion of privacy said, in world A, the British Doctors study was never carried out. In world B, the British Doctors study was carried out, and it asked, do I know something new about you in world B that I didn't know in world A? Okay, and unfortunately, the answer was almost always yes. Differential privacy can also be viewed as comparing two counterfactual worlds, but worlds that are different in a more subtle way. So in world A, the British Doctors Survey is carried out, but without your data. And in world B, the British Doctors Survey is carried out with your data. More generally, we're comparing worlds in which the same analysis is run. The only difference is whether your data was included in the data analysis or not. And what differential privacy asks for informally is that it should be almost impossible to distinguish which of these two worlds we're in. That there should be no way to learn there should be no way to learn substantially more information about you if your data was included in the data analysis compared to what we could learn about you if the same analysis had been carried out without your data. And in this way, it's sort of disentangling secrets that are yours to keep, secrets that are encoded in your particular data from, facts about the world that are somehow, not your secrets to keep and not something that we should hope to protect. So I won't say too much more about the definition, but let me sort of point out that sort of the conceptual breakthrough here, the definitional breakthrough happened back in 2006, I guess, about 15 years ago now. And since then, there's been sort of a vibrant academic research agenda of figuring out what are the kinds of analyses that you can do subject to this formal notion of privacy, and what are the ones you cannot. And many people, when they first hear this definition, they sort of are willing to agree that it's a good privacy definition. If I can't learn anything with your data that I couldn't learn without your data, then that seems like I'm protecting your privacy, because people are often willing to agree that if I have no access to your data at all, then information that I reveal shouldn't be viewed as disclosive of your privacy. But a common concern that the definition is too strong, that much like the sort of idealized definition that we talked about with the British Doctors Survey, maybe this is a good definition of privacy, but maybe it doesn't let you do anything useful with data. And the happy thing is that that's not true. And at a high level, it turns out that almost any statistical task that can be carried out without differential privacy can be carried out with differential privacy. Where here, what I mean by a statistical task is something whose success or failure is defined with respect to a distribution, a population, rather than with respect to a particular person's data or a particular data set. Right, so this covers classical statistics, things like regression. It covers almost all of machine learning and many other things. This is not to say that privacy comes for free. In fact, there are sort of very crisply understood costs for imposing privacy constraints, but they manifest themselves in the form of the need for more data. Right? If there's some task that you can perform without privacy protections, then typically if it's a statistical task, you can perform it with privacy protections, where you will need more data than you needed before, or you will need to settle for diminished accuracy. But we can exactly understand what these trade-offs are. And so there's a cute little algorithm here that maybe I won't talk about now for the sake of time, but offline or after the talk, happy to walk through like a simple example of how you can conduct an analysis subject to the protections of differential privacy. And one of the ways in which privacy has been a success story that sort of these other areas that aim to embed social norms into algorithms might aspire to is that for about 15 years, this was a topic of academic research, mostly mathematical research. So this is something that came out of theoretical computer science, and most of the papers in this literature up until maybe 10 years ago, or sorry, for the first 10 years up until maybe 5 years ago, were mathematical papers, and that the primary product of these papers was a theorem. But in the last 5 years, this has started to make the transition from just a theoretical curiosity to an actual technology. And so now a lot of the action in differential privacy is actually at big tech companies, places like Google and Apple and Amazon, that are actually deploying this technology widely. And one of its biggest tests is just around the corner. The 2020 decennial census in the United States is going to, for the first time, release all of its statistical products subject to the protections of differential privacy. Okay, and so this is the sense in which I think privacy is the biggest success story thus far in this broader research agenda, in that it has sort of grappled, I think, successfully with definitions, and it has found crisp definitions that capture a lot of what we often mean by privacy. We've spent a lot of time thinking carefully about the implications of those definitions, in particular the costs and trade-offs of imposing them. And then finally, this has made the transition from from the whiteboard to an actual technology. Okay. So now let me spend a little bit of time talking about algorithmic fairness, and let me lead by saying that we're not nearly where we are with privacy with fairness, and part of this is because the algorithmic fairness literature is more than a decade behind the differential privacy literature. But we already also know that the study of fairness is going to be more complicated than the study of privacy. So first of all, by and large, differential privacy has become an accepted notion of privacy, at least in technical communities. In algorithmic fairness, like, we don't agree on definitions. There are almost as many definitions of fairness as there are papers in this literature. That's not quite true anymore, but maybe it's not a horrible cartoon. And we also know that we're not going to find like a definition that captures a huge number of the use cases, in that we've already identified sort of individually reasonable definitions that are mathematically incompatible with one another. We are beginning to understand the trade-offs involved in particular definitions, both trade-offs with things like accuracy and with things like other notions of fairness. But algorithms play a much smaller role in fairness writ large than they do in privacy, in the sense that individual algorithms for, say, credit applications can exacerbate unfairness, but unfairness is sort of a bigger systemic problem generally. And so what we really need to understand are dynamics, in the sense that, if we change our algorithm to, do something a little bit different, how will that interact with, the rest of society in a way that, will have presumably complicated feedback loops and unpredictable changes. And that's something that's important that we're only really beginning to think about. Nevertheless, I think we're off to a good start. And let me just maybe remind you of, a couple of headlines that you might remember, just to sort of point out that this is really a pervasive problem. These are headlines that were salient, like the week in which our book was released. But, I could have picked two more recent headlines. These really come out, just about every week now. And the first is about an algorithm that was used for targeting healthcare that was discovered to have racial bias, in the sense that if I had two similarly sick patients, one white, one black, the algorithm was likely to recommend sort of more expensive interventions for the white patients than for the black patients. And the other of which was about an algorithm that was automatically approving people for credit cards and setting their credit limits And it was found to have gender bias in the sense that you could find two people who were really very similar in terms of their credit scores. Some of them were spouses, they had joint accounts, and the algorithm would systemically give higher credit limits to men than women. And so I want to think about, like, first of all, why might this arise? Because a totally reasonable thing to think at first is that, something like, racism or sexism, these are human attributes, and maybe by like removing the human being from the decision-making pipeline and replacing it with an optimization algorithm that is just optimizing for accuracy, I will perhaps like definitionally have no gender or racial bias. And let me walk through a cartoon example to convince you that, things are more complicated than that. So this is a two-dimensional cartoon, but the things that it illustrates are true of real machine learning. So suppose I wander over to the admissions office at Penn and I say, look, let me, I'm from the computer science department. Let me save you a lot of work. Let me help you automate the admissions process. And in this cartoon, maybe there's only two features that applicants have in their application: SAT score and GPA, which are plotted here in this two-dimensional grid. And suppose there's some verifiable label that we're trying to predict, okay? Some criteria for a successful admissions decision. It doesn't matter what it is, just that it's measurable. So maybe this is data collected from past applicants, and the positive examples were people who graduated in at most 5 years with at least a 3.5 GPA, or maybe they're people who donated at least $10 million within 30 years of their graduation. Doesn't matter what specifically we're trying to predict for this example, just that it's measurable. And let me assume away all sorts of obvious forms of bias to show you that just the sort of principles of machine learning can cause it to creep back in. So you might worry in this example that the labels have been measured incorrectly. Like maybe maybe we're sort of better at measuring the labels for one group of people than for another. Let's say that's not true. The labels are like, correct. You might also worry that, maybe we only have these labels for the people we've previously admitted, and so this doesn't really represent the underlying population, and it's sort of encoding the bias of past decisions of human admissions officers. Let's wish that away too. Let's say these are actually labels from the actual underlying population of applicants to our university, and still there can be problems. So there's going to be two groups here. Okay, right now you're looking at the green group, but there's also an orange group. And I want you to notice a couple of things. So first, the green group, slightly fewer than half of them are qualified for admission, by which I mean there's more minuses on this slide than there are pluses. Second, there's a pretty good, although not perfect, decision rule that can distinguish the positive examples from the negative examples, right? And it's this line. I can draw this line through space, and by and large, the positive examples are above it, and the negative examples are below it. And so if I trained a machine learning algorithm that tried to find a linear decision rule, it might find this one. Okay. Now there's also this other population, the orange population, and I want you to notice a couple of things about them. So first of all, they're a minority, by which I mean purely in the mathematical sense that there are fewer of them. There are fewer orange points than there are green points. Another thing you might notice is that these orange points are sort of systematically shifted downwards on these axes. And so they appear to have sort of systematically lower SAT scores. And you could tell any number of reasons for why this is. For example, maybe the green population is wealthier and takes the SAT 3 times. They take SAT tutoring classes. They report the highest score. Whereas the orange population, is less wealthy. They take the exam once cold and report that score, right? That would naturally lead to a lower distribution on scores. And yet, despite that, the orange population is not less qualified, right? We don't care about SAT scores per se. We care about labels. We only care about SAT scores insofar as they are predictive of these labels, this metric for college success. And in fact, the orange population is actually better than the green population. Right? They're better in two ways. First, on average, they're more qualified, right? Exactly half of the orange population is qualified for college, whereas fewer than half of the green points were qualified. And second, it's actually even easier, at least on this sample, to tell who's who, right? Like there's now a linear decision rule that makes no mistakes at all. And so despite having a different distribution on SAT scores of these two populations, right, from the perspective of the admissions officer, the orange population is actually the better one. They're more qualified on average, and it's easier to tell who's qualified and who's not. And now here's both populations together, okay? And let's suppose I ask my machine learning algorithm to find the best linear decision rule, the line it can draw through space that will make as few mistakes as possible using SAT score and GPA. And I'm careful about introducing, I don't want to introduce any kind of like racial bias into my algorithm. And so I don't give the algorithm access to the colors. The algorithm can't tell the difference between a green point and an orange point. It's purely gonna find the best decision rule using SAT score and GPA. And so what's gonna happen? Well, it's not hard to see that the best linear decision rule is just the linear decision rule that fits the green population. And in particular, it will reject every single member of the orange population, even the qualified ones, despite the fact that the orange population is more qualified on average. And why is that? Well, what would happen if I moved this decision boundary downwards to better fit the orange population? Well, it would make fewer mistakes on the orange population, but it would make more mistakes on the green population. And because the green population is the majority population, because there are more green points, that wouldn't be worth it, right? Since the algorithm is trying to minimize its average error, well, the average is biased towards the majority population. And maybe there's one more thing I want you to take away from this example, which is that there's sort of an obviously better thing you could do, right? I could learn a different decision boundary for the orange points and for the green points, right? If I did that, I would make fewer mistakes. So this would be better from the point of view of the objective function, from the point of view of the designer of the machine learning algorithm. And at least intuitively, it feels more fair in the sense that I am by and large making correct decisions now on both populations, whereas previously I was disproportionately making my errors on the orange population. And so the two takeaways here are first, that bias can creep into an algorithm sort of without it being baked in, just from the sort of basic principles of machine learning, in that whenever I ask an algorithm to optimize for some average statistic, like average error, if it cannot, with the same model, optimally fit both populations, it will fit the majority population, because majority populations contribute more to averages. And second, although it might seem like a good idea to restrict the inputs of the algorithm if you want to avoid racial or gender bias, to not allow the algorithm to use group membership, that can actually be quite a bad idea. And this is an example of what we think about as sort of a bad family of definitions, focusing on the inputs to the algorithm that are actually encoded in bodies of law, in housing and financial regulations. You're forbidden from using racial information, for example, in making decisions. And that can actually be harmful because it makes it difficult to even measure group disparities. Whereas a better family of definitions focuses on what the algorithm actually does, the outputs. And so let's briefly think about how we might think about unfairness. And one starting point is to ask the question, who was harmed by the mistakes of the algorithm? And one answer that you might arrive at, not the only one, but one answer, is that In this example, the people who were harmed were really the applicants who were qualified, but who like ideally should have been admitted, but were mistakenly rejected. And if you like that answer, then you might start thinking about the false negative rate, sort of the rate within each population maybe at which the algorithm makes these mistakes in the harmful direction, the rate at which it rejects people who are actually qualified. And maybe that fits some of our intuition as to why this blue classifier was unfair. The rate at which it is making errors in the harmful direction is like much higher. It's 100% in the orange population compared to the green population. And so this is indeed a very popular notion of fairness in the literature. And it's one of a collection of definitions that are called statistical fairness definitions that work as follows. You partition the world into groups, often according to some protected attribute like race or gender. You pick your favorite statistic of a classifier like false negative rate, and you ask that it be approximately equalized across groups. And so is this the definition we want? And if you think about it a little bit more, perhaps this doesn't really capture everything we wanted. And here's another cartoon example that actually, again, manifests itself in real problems. Suppose that I want to protect people along two axes, not just race, but also gender. So let's say I've got two groups of people, blue and green, and men and women. And I say, okay, I would like to equalize false negative rates across blue people and green people, and also across men and women. Okay, and now we run our machine learning algorithm, and it will find a model that is very good according to this metric, but it will not necessarily satisfy any other constraint that we didn't explicitly specify. And so, for example, it could come up with the following solution. It could admit students if and only if they are blue men or green women, and reject them otherwise. And that's not a very good promise, because in particular, if you happen to be a green man, the algorithm is going to reject you with certainty. If you're qualified, it will make the mistake in the harmful direction with certainty on you. And so the problem is that a classifier that equalizes false negative rates doesn't really offer a semantic promise to you as an individual, because the word rate in false negative rates assumes that you are a uniformly random member of your population. It's an average over people. And so if you have reason to believe otherwise, because, for example, race, both your race and your gender, it can promise you nothing. Okay, so I'm running low on time, so let me sort of fast forward through the next bit, which is just to sort of explore what else is possible in the sort of space of thinking about fairness definitions. And that, if I had time, I would talk about one particular way in which you can give semantics to particular people, but it's definitely not the right definition of fairness. And, I don't think anyone has the right definition of fairness. We're sort of in this pre-definitional age in the fairness literature where we haven't yet found the right way to think about things. But it's an example of sort of the design space. That is, even though machine learning is inherently statistical, it is still possible to enforce guarantees that will provably hold and provably allow you to do different kinds of statistical analyses that can offer semantic promises to individuals. And figuring out the right way to do this is, I think, one of the most interesting parts of the sort of research frontier right now, really sort of thinking about definitions. So, okay, I would have told you about one of them, but I won't. Let me just end by sort of saying, okay, I've walked you through a couple of case studies, one in privacy, one in fairness, sort of thinking about definitions. In the book, we think about other stuff as well. We think about the role of dynamics and the role of of game theory in particular in thinking about what will be the sort of systemic level effects of local algorithmic changes. And these can often be counterintuitive. And so it's important to think about how small tweaks to apps and algorithms can, not only what they will do myopically, but what they will do, as an economist might say, in equilibrium. And we also talk about maybe surprising connections between some of these mathematical approaches to things like privacy and unexpected areas like the statistical crisis in science, the sort of reproducibility crisis that you might have heard about. But since I'm on my last minute, let me end there, and thank you for having me.
Hey, thanks so much, Aaron, for a fascinating talk. It was really great to hear from you. As you said, we're basically out of time. I'll just ask one question from the chat. Someone was asking that what options do we have when we are restricted by either legal norms or social norms when trying to address fairness? Are there other options that we have?
Yeah, so I'm not sure I entirely understand the question, but typically, like, we've got a lot of options. The thing that the thing that we sort of suggest that you do is start by, very clearly enunciating what you mean by, for example, fairness. This will mean different things in different places. What are the harms that you want to prevent? And then trying to embed them into your algorithm design. Now, it is often the case that the solutions that would work best might run counter to legal regulation. So, for example, in privacy, existing regulations like HIPAA are sort of tied to this old idea of anonymization that we now know doesn't really work. And similarly, fairness regulations often operate by precluding inputs, by saying you shouldn't think about, you shouldn't even give the algorithm access to protected attributes, while saying relatively little about outputs, which again, I think is the wrong way to do things. We should, this will be a longer term thing, but we should work to influence policy. These are laws that I think can be better written and should be.
Great. Thanks so much, Aaron. Thanks again so much for joining us. And thanks for everyone who logged in to attend this talk. I just wanted to say we do have several interesting talks coming up related to bias, and including one from John Kleinberg on October 23rd. And you can just sign up for the Computation Society Initiative mailing list to get up-to-date announcements on everything. But thanks again for joining us, and thanks